Okay, so let's start our lesson for today. So I'm going to start with doing an example from regular singular point series solution, and then we'll just move on to chapter 6. Okay, are you ready? Yep. Okay, so let's go. So here I have a question typed for us to work on. So I kind of broke it down into parts so that way you get to see what are the requirements for this particular question. Okay, so here first we want to show that for this given differential equation, x naught equals 0 is a regular singular point. So that should give you a hint that our series solution for the next part, which is the last part, it's going to be the summation an x to the n plus r, okay, which is different from a series solution near ordinary points. So make sure you note those two differences. Okay, so having said that, let's do the first part. So this is still continuing 5.5. So just one last example before we say goodbye to 5.5. So here's a differential equation, second order function coefficients. We want to show that x naught is a regular singular point. So from previous lecture, how do we show x naught is a regular singular point? Right, so we can compute those Euler coefficients, and then that will help us to do second part of this question. So we know by limits, we find beta, which would be the limit as x approaches x naught, which is 0 in this case, and we take the limit of x times q of x, so this is p, this is q, and this is r. So that would be q of x, which is x over p of x, that's x squared. And then x squared over x squared, that's just 1. Limit of a constant is a constant. So this limit is 1. And then we can find another Euler coefficient, which is gamma. That's going to be the limit as x approaches 0 of x squared times r of x, which is x minus 9 in this case, over x squared. And what is this limit equal to? Right, so this is going to be negative 9. Okay, so part 1, we have shown that. So since these limits are finite, you just write a sentence, x naught equals 0 is a regular singular point. So that's the conclusion for the first part. Now for the second part, we want to show what we want to write out the corresponding Euler equation. Okay, so we already did half of the work for that question. So Euler equation is in this form, x squared y double prime plus beta x y prime plus gamma of y equals to 0. And we know what these coefficients are, beta and gamma. That's from part A. So plugging those in, we have x squared y double prime plus 1 x y prime minus 9y equals to 0. So that's the corresponding Euler equation. Any questions? Now for the third part, we'll just continue this and compute the root by writing out the initial equation, and then we'll hold on to the root until the very end when we write out the series solution using one of the roots. So in this case, you will see part 5, it says series solution corresponding to the larger root. So we're going to use this for part 5 again. So part 3, so what is the corresponding initial equation for this? What do you guys have? Okay, anyone? What do you guys think? What's the initial equation for this Euler equation? Yeah. So make sure you guys know this for the test, okay? So um, I'm not getting a lot of participants, but hopefully you guys are following me. Let me know if you guys have questions. So we have this as our initial equation. Now from here we start solving for r because this is a second degree polynomial. So we expand this, we have r squared. So we have minus r plus r, they will cancel out. Minus 9 equals to 0. So then r is going to be plus and minus 3. So we have the roots for r. Okay, so that completes part 3. Now, part 4, we want to compute the recurrence relation for the coefficients. So this is when we start doing the series solution. So we're going to assume, because this is a regular singular point, we're going to assume that the solution form is going to be y equals the infinite sum n equals 0 to infinity an x to the n plus r. And if I were to write out some of the term of this series, I'm going to factor out x to the r, and then we have the sum n equals 0 to infinity an x to the n. And if you were to write that as power series expanded form, you would have x to the r times a0 plus a1 x plus a2 x squared plus and so on. So that's how the solution would look like if you were to expand it out and write out some of the terms, or if you want it in a condensed form, then you can just leave it in this form right here. But we like to use this one because we're going to write out some of the terms for this power series solution. So if we assume that's the solution, so we're going to compute its first derivative, second derivative, and then plug it into the original equation. So those are the next steps. So y prime is going to be the sum n equals 0 to infinity. So we take the derivative of this formula. We have n plus r times an x to the n plus r minus 1. And then we take its second derivative. That would be the sum starting at n equals 0 to infinity n plus r times n plus r minus 1 an x to the n plus r minus 2. So these are the expressions for the first derivative and second derivative. Now let's look at the original equation. So the original equation is x squared times y double prime. So we have, so let me just copy it first. So we were given x squared times y double prime plus x times y prime plus x minus 9 times y equals to 0. So let's just double check if I copied it right. Yep. Okay. So let's plug this in. So we're going to plug in these summations into our original equation. So we will have the sum. So I'm going to ignore the indexing because it's okay. I showed it to you guys why it's okay, because it gives you the initial term, which we call it the initial equation, which we can get it from right here, Euler equation. So we don't need the initial terms anymore from the series solution. So I'm going to happily ignore the indexing and just write out the sum n plus r times n plus r minus 1 an x to the n plus r minus 2, and I have an x squared in the front. For the second term, we have x times the first derivative, so that's going to be n plus r times an x to the n minus n plus r minus 1. And then for the third term, well, you have to distribute the y, so I forgot to do that, but I'm assuming you guys can follow me. If not, let me know if you guys have questions. Plus x times y Well, y is the assumption we're making, so that's an x to the n plus r minus 9 times the sum an x to the n plus r, everything equals to 0. So that's the setup. Now we're going to simplify this just a little bit by combining powers. So I'm going to go ahead and move this one inside and combine it with that. Move this one inside, combine it with that. And then this one will go inside as well. And the 9, you can keep it out there or put it inside the summation. Not a big deal. So continuing with that, we have the sum of n plus r times n plus r minus 1 an x to the n plus r. So the minus 2 and the plus 2, they cancel out. And then for the second summation, as you push the x inside the summation, that negative 1 power of x will drop. So you have the sum n plus r times an x to the n plus r. And then the next one, as we push the x inside, it's going to add 1 to the exponent. So we have an x to the n plus r plus 1 minus 9 times the sum an x to the n plus r equals to 0. So that's the next step we have. Okay, so after this, what do? We want to have the powers of x to be k plus r. That's what we want. So for the first one, if we want the power to be k plus r, so we're just going to let n to be k. The second one also n to be k. And the third one, well, we need to modify. We want k to be n plus 1, so that n is going to be k minus 1. And the last one, we can let n to be k. So the first, second, and the third is nice, but the third one changes. Okay, so if I do these transformations, kind of swap them, we have the sum n plus r times n plus r minus 1. Oh, okay, so no one caught me, right? I'm supposed to put all of these in terms of k, not n. Are you guys paying attention? Okay, so we have k plus r minus 1, and then we have a sub k, x to the k plus r, plus the second one also n is k, so it doesn't matter. So we just have k plus r, a sub k, x to the k plus r. The third one we're going to have to change a little bit. So we have plus the sum a sub n is going to be k minus 1, x to the k plus r, minus 9 times the summation a sub k, x to the k plus r equals to 0. Okay, so not so bad. Well, now they all have x to the power k plus r, so I can factor that out and combine all the coefficients into a single summation. So that's the next step. So we have the sum, and all the coefficients of x to the k plus r is going to be k plus r minus 1, a sub k, and then plus k plus r, a sub k, plus a sub k minus 1, minus 9, a sub k, everything times x to the power k sub k plus r equals to 0. Okay, so that's a success. So we're now ready to write down our recurrence relation. So we want the coefficient of x to the k plus r to be 0, which is all of this. We want this to be equal to 0 so that we can solve for the highest subscript. And that will be our recurrence relation. And the highest subscript on this, it's going to be a sub k. So we have a sub k is equal to, so I'm going to move a sub k minus 1 on the other side. That would be negative a sub k minus 1. everything over k plus r minus 1 plus k plus r and then minus 9. So that becomes the recurrence relation. We're going to simplify this when we plug in r. So the next part of this question, so part 4, compute the recurrence relation for the coefficient. So we have the recurrence relation. This is it. So this is part 4. Now the last part, well, before I move on, any questions up to this point? Are you guys okay? Okay, so, all right. So moving on. So since we have the recurrence relation, now we want to find at least one solution, right? We want to find one solution that corresponds to the larger root with using a0 as 1. Okay, so that would simplify the answer a little bit more. So for part 5, find the series solution corresponding to the larger root with a0 as 1. So for the larger root, what is the larger root for this question? So we have r equals, right, so 3 and negative 3, the larger root will be 3. So for part 5, r equals 3, this is the larger root. So our recurrence will become a sub k is equal to negative a sub k minus 1 over plugging in r equals 3. We have k plus 3, and then k plus 3 minus 1, that's k plus 2, plus k plus 3 minus 9. And then this would simplify, so this is nice. So we have negative a sub k minus 1 over, let's see, what will this simplify to? So we have k squared, 2k, 3k, that's 5k, plus a k, that's 6k, and then 3 times 2, that's 6, and plus 3, that's 9 minus 9. So they cancel out. So this is the simplified recurrence relation for r equals 3. And now here I can simplify a little bit more so that computing the coefficient is simpler. So we can say a sub k will simply be negative a sub k minus 1 over k times k plus 6. So that's pretty simplified. Now let's find some coefficient. So we were given a0 is 1. That was given on the problem. So let's go ahead and compute a few more coefficients. And let's see if the question says how many terms. So it doesn't say how many terms. So I'm going to go with 2 more. So we have at least 3 non-zero terms. So let's plug in k equals 1. So we will get a sub 1. So if k is equal to 1, we have negative a0 over 1 times 6 plus 1, that's 7. So that would just give us negative 1 over 7. So we have another non-zero term. So we have 1 here, and we have a sub 1. Let's go for one more, like k be 2. So we get a sub 2. So a sub 2 would be negative a sub 1 over k is 2, so that's 2 times 6 plus 2, that's 8. And this would give us negative a sub 1, which is negative 1/7. If I plug that in, I have positive 1 over 2 times 8 times 7. What you multiply it out and see what that is. I'm just going to leave it like that, okay? Now let's write out the solution. So we know that our solution is going to be y equals x to the r. So I'm going to write out the expanded form instead of the closed form. a0 plus a1 x plus a2 x squared plus so on, right? So that's one of the solutions. So let's call it y1. So y1 is going to be x to the r. Well, r is 3 in this case, times a0, that's 1, plus a1, that's negative 1/7. So this would be minus 1 over 7x plus a2, that's 1 over 2 times 8 times 7 x squared, and so on. So that's one of the solutions to this differential equation. And of course, your smaller root will give you y2, and together with y1 and y2 will form the general solution. But we don't have that much time to compute the general solution, so we just compute solution corresponding to the larger root or the smaller root, so just enough. Okay. So there you go, another problem for 5.5. Any questions, guys? Are we doing okay? Okay, so to have more practice, I would say finish up web work. I think it has section for 5.5. Finish those up, see how you feel, and then if you want more practice or you want to do some really good examples to practice, do the ones from the textbook. They're really good. I like those questions, so you probably know that by now. So do this question. They're really going to help you to understand these kind of solutions. All right, so that's the end of chapter 5. We're not going to go anymore on series solutions on that. We're moving on to the Laplace transform. So first we want to talk about what is the Laplace transform. We're going to define it, and we're going to do some computation, do a little bit of theory, and then we'll see second order differential equation solutions using the Laplace transform. So that's where we're headed. So chapter 6. So chapter 6 is the Laplace transform. So this is a very short chapter in this course. We're just going to do 6.1 and 6.2. So we're not gonna do much, but these are really good topic to spend time on. Okay, so let's start off with 6.1. So 6.1 is the definition of the Laplace transform. Okay, and sometimes Laplace transform is also called an integral transform. So if you hear that terminology, we're also talking about Laplace transform. It's also known as an integral transform. Okay. So let's define what is Laplace transform. So by definition, we define the Laplace transform as an improper integral So you have seen improper integral in your past experience in a calculus course, right? You treat improper integral as a limit, right? So hopefully you're able to recall that moment and use it here when we're doing Laplace transform. So the Laplace transform of a function f of t, so this is the notation. This curly L indicates we're talking about Laplace transform. So it's a very special, it's not just writing L like that, okay? You have to write it with passion. You have to say the Laplace transform, okay? So something that you can probably spend time on, making a really good Laplace transform looking L. Okay, so having said that, the Laplace transform of a function f of t of s is equal to the improper integral 0 to infinity f of t times e to the negative st dt. And what it outputs is a function of s. So that's big F of s. So let's analyze this for a moment. So what are we doing? We're taking this machine, okay? So this machine is called the Laplace transform. What does it do? It takes the function, whatever you input. So I'm inputting f of t, sorry. I'm inputting this function into my Laplace machine, right? I'm calling it a machine. And what it's going to do, it's going to put the function in here, inside the integrand, and multiply with this e to the negative st. Well, this function e to the negative st has a name. It's called the kernel. It's the kernel of the transformation. So if you took linear algebra, you probably had this. You probably had seen it, the kernel of something. But here it's the kernel of this transformation, this particular transformation that we're working with. So what it does, it takes this new function f of t, multiplies with this kernel, and integrates on the real line 0 to infinity, respect to the variable t, so that when you take the limit as t goes to infinity, you have a function in terms of s. That's what this new function is. So you input a function of t, your output is it completely transformed into a function of another variable, which is s, okay? So that's the idea with this transformation. So think of this as a new tool in your pocket. Just like integration is a tool, differentiation is a tool, Laplace transform is another tool that you can add to your, I don't know, let's call it knowledge of math, okay? So what's so nice about this tool? Well, this is a very nice operator. It's a linear operator, okay? So cool thing about Laplace transform is that Laplace transform, LT for shortcut, is a linear operator. And we like linear operators because just like derivatives, if you take the derivative of, say, so for example, if you take the derivative of sum of two functions, what the linear operator does, you can take the derivative of individual functions and add them up, right? Sum of the derivative is the derivative of the sum. That's kind of like a song singing in your head. So same thing with Laplace transform. If you take the Laplace transform of two functions, say f and g, you can split it up and you can do Laplace transform of f and then add the result with Laplace transform of g. So I'm going to come back to this later and prove it to you why Laplace transform is a linear operator. So just like derivatives and integration, this is a very nice tool we can have in our pocket. So any questions so far? Is it making sense a little bit? Okay. So let me do an example to help you do some computation with this new operator, and hopefully you will feel comfortable and recall your experience in calculus course. Hopefully you had good experience. So let's look at the first example. So let's do Laplace transform of a constant. Okay. So what if I want to find the Laplace transform of the constant 1. Okay. So if I want to find the Laplace transform of 1, well, by definition, I just plug it in, right? So it says you take the function and you integrate from 0 to infinity. My f is 1 times the kernel, which is e to the negative st dt. So you're integrating over the t variable. That means s is treated as a constant. And whatever function it comes out, that's your variable, which will be s. So how do we integrate this? Well, we integrate this But before we integrate, we have to treat it as a limit, right? Why do we have to treat it as a limit? Right, because we have an improper integral. We have infinity. So we're going to say, okay, let's take the limit as, whatever variable you like. I like t. Big T goes to infinity. We're integrating from 0 to t, e to the negative st dt. And then we just go ahead and integrate and take the limit as t goes to infinity. So what is this integral? So the limit as t goes to infinity, so s is a constant. So if I integrate this, think of it as you're integrating e to the 2t, with respect to t. What's the integral of that? Yeah, right? So if s was a 2, you would say to the negative 2t over 2. So that's the integration of this, and then we take it from 0 to t. So we integrate, and now we take we apply the fundamental theorem of calculus and take the limit. So we plug in the upper limit first, and then the bottom limit. So we have the limit as t goes to infinity of, so plug in big T into little t. So sorry, I'm using t and t. So next time we'll switch it to another variable so I don't have to repeat t and a little t. It's weird. So, okay, so I'm plugging in big T for the little t. So we have e to the negative st over negative s minus, right? When you plug in the bottom limit, you have to subtract, minus e to the 0, which is 1, minus 1 over s, so it's plus 1 over s. Now we're ready to take the limit. So as big T goes to infinity, what happens to this right here? What happened to that as you take the limit? It goes to 0. So as you take the limit, this goes to 0. So we're left with 1 over s, because limit of a constant, it's just the constant itself. So we can see that the Laplace transform of the constant 1, it's going to be 1 over s. So you see how you plug in a function of t, well, in this case it's just a constant, but your output is a function of s. So this is what we call the big F of s. So in sum, we can say, so the Laplace transform of any constant, it's going to be the constant over s. So that's why we can conclude from this computation that we just did. So this is something you want to remember. Or if you ever forget, just make sure you remember the definition, and then you can always compute it very quickly. So I wouldn't say memorize, but it's good to kind of know it quickly. But not a big deal if you forget. Well, so what will be Laplace transform of 3? Absolutely, 3 over s. So you can just kind of write that down very quickly without even applying the definition. But hopefully it makes sense. Let's do another one. So here is our second example. So what if we want to compute the Laplace transform? So find the Laplace transform of e to the at. Okay, so a is a constant. Oh, so another thing I need to mention, we want to make sure that when we take this limit, going back to the first example, we want to make sure for this part that s is greater than 0. Because if s is less than 0, then we get infinity. It's going to diverge. So you want to, oh, sorry. I just said something and I wrote something else. We want s to be less than 0. No, wait, hold on. No, we want s to be positive. Sorry, I'm confusing you guys. Sorry, guys. We want s to be positive, so bigger than 0. So why do we want s to be positive? So let's think about this for a while. What happens if s is negative? Right, so you'll have, so s is negative, and that negative sign, you will have e to the negative negative st, because s is negative, and then that turns into positive. And then as you take the limit, as t goes to infinity, then all of this will just go to infinity. So we wouldn't have what we want to have, which is 1 over s. So that's why we must restrict that s is positive. So as long as s is bigger than 0, this limit guarantees to go to 0, so we have 1 over s is the Laplace transform. So we need that restriction. Okay, so let's do the second example. So we want to compute the Laplace transform of e to the at, and a is a constant. So it could be any constant. So let's check this out. So we want to find, so we know the Laplace transform of any function, it's going to be the improper integral. So in this case, our f of t is e to the at, so we're doing the Laplace transform of e to the at. So we have the improper integral 0 to infinity e to the at times the kernel e to the negative st dt. And then the next step is to just play around with this, and then hopefully we can integrate this successfully. So I'm gonna join the exponent because we can do that by laws of exponents. So we get the following. We have 0 to infinity e to the a minus s to the t power dt. Any questions? Okay, so what is this integral? Well, s and a, we're treating them as a constant, right? So you can change this to an improper a limit question and then take the integral. So we take the limit as, let's say a goes to infinity. So I'm choosing a now instead of big T, so that way we don't have t and t all over the place. So we have a e to the a minus s to the t dt. So what is this integral? So e to the a minus s times t over a minus s, and we're taking it from 0 to a. Okay, so now let's do this limit. So we have the limit as a goes to infinity of, so as I plug in big A for t, so we have e to the a, oh no, not for that one, we have a minus s times a over a minus s minus e to the, as I plug in 0 for t, that's 1. So we have 1 over a minus s. Okay, so now what happens? We want this limit to go to 0, right? So that we have convergent. So here's how it's going to go to 0. If we impose the condition, as long as s is greater than a. You agree? If s is always greater than a, then this limit, as big A goes to infinity, it will be 0. Do you agree? Okay, so we're going to impose that condition so that this limit goes to 0. So what we're left with is negative 1 over a minus s, as long as s is greater than a. Well, now, this is the Laplace transform of e to the at. But if you look at the table for Laplace transform in 6.2, it's just in the reverse order. So what the textbook does, it pushes the negative on the bottom and distributes. So to write it nicely, Laplace transform of e to the at is going to be 1 over s minus a, as long as s is greater than a. So that's the Laplace transform of the exponential at. So any questions on this? So you can find Laplace transform of almost any function, even piecewise functions. So that's possible as well. So you will have some homework question where you'll be computing Laplace transform of sine, cosine, and probably some other functions that we're more familiar with. Now, here's another problem that you can think about. Well, how would you compute the Laplace transform of the function t? So I'm not going to do it fully. You can check it for homework. What do you guys think? So, well, that will be the answer, right? So my question was, how would you approach this question, this problem? So you gave me the answer probably. I don't remember the answer, but it sounded like a function of s, so most likely an answer. So what do we want? Well, we want f of t is t. So if you use the definition, the Laplace transform of the function t, by definition, it's going to be 0 to infinity f of t, which is t, e to the negative st dt. So the question is here, how would you compute this integration? Right, so the key here is to do by parts. So you would integrate by part. Integration by parts. And then you'll get a huge expression, take the limits, most of them will tend to 0, and then whatever is left over, that's your Laplace transform. Okay, so you can handle this, right? You will do this for homework. So that's for you. All right, so the next one I'm going to do is, let's see. So I do want to do one more example. So what about for piecewise function? So I want to do a piecewise function. So what if, so before I do that, let me give you the theorem that we should talk about before moving on to piecewise Laplace transform. So here's a theorem. Oh, I copied the table here as well, so I'll share that with you in a few seconds. Not yet. So if you look at this theorem, this is from 6.1. Very useful theorem. So we'll just chat about it a little bit, and then I'll do an example. So what does this theorem tell us? Well, it tells us two things, okay? So it says, suppose that f1 condition. F is a piecewise continuous. So this is important. Piecewise continuous on the interval 0 to a. Okay, so some positive interval for any positive a. Okay, I said that. And then second condition, the absolute value of f is less than or equal to some k times e to the at, where t is greater than or equal to m. In this inequality, a, k, m are real constants, and m and k are positive. Okay, so that's important. Then the Laplace transform of this function is f of s, defined by equation 4, which I gave you definition right here. So what the theorem really says in sum is that if you have a piecewise continuous function and if you have bounded function, so this is bounded. Okay, so if you have a bounded function and it's piecewise continuous, then it is possible to compute its Laplace transform. So that's the idea behind this theorem. I'm not going to go through the proof because we don't have that much time, but you can definitely, if you want to see how things work, you can read through the text. It's not so long, it's pretty nice. So this is what it's saying. So let's look at a function, okay? So here's an example to illustrate. So let's find the Laplace transform of the function f of t, which is a piecewise continuous, okay? So we have 1 on the interval 0 to t less than equal to pi, so less than pi. And then we have the function 0 on the interval pi to infinity. So that's what it means to be piecewise continuous, meaning on certain interval you are continuous, but piecewise continuous. So let's look at the graph of this function and then we'll compute its Laplace transform. So if I were to graph this piecewise function, so I'm going to do my best to graph it. So remember, your domain is 0 to infinity. So we have nothing on the negative real. So here is our xy plane. This is the positive infinity. So on 0 to pi, we have the graph f of t is equal to 1. So f of t is equal to 1. So we have 0. No, at 0 it's going to be at 1. And then at pi it's going to be at 1, but open circle. So that's 1. And then from pi to infinity, we just have the constant 0 function. So from here to on, we have the 0 function. So here we have a piecewise continuous function on an interval 0 to infinity. And the theorem says if that's the case, and if f of t is bounded, this is definitely bounded, so we can find the Laplace transform. So the Laplace transform, by using the definition we gave earlier, the Laplace transform f of t is going to be the integral from 0 to infinity f of t times e to the negative st dt. Well, what's my f of t in this case? That's this piecewise function. So let's write it out. For this particular function, we split the interval into 0 to pi and then pi to infinity. So we have the integral from 0 to pi plus pi to infinity. And on the interval 0 to pi, we have the function 1 times e to the negative st. And on the intervals pi to infinity, you have the function 0 times e to the negative st dt. So that's how it works. So we can still take the Laplace transform of this graph because it's piecewise continuous and bounded, so it's allowed. Well, now let's integrate, right? The integration isn't so difficult. So for the first one, e to the negative st, we can just go ahead and integrate. We have negative 1 over s e to the negative st going from 0 to pi. And the second integral is just 0, right? 0 times whatever is 0. So I can ignore that part. So if I plug these upper limits and bottom limits, we have negative 1 over s e to the negative s pi minus 1 over s e to the 0, that's just 1. So if I simplify this, this would just be 1 over s minus 1 over s e to the negative s pi, and just putting all of this together nicely, we have the Laplace transform to be 1 minus e to the negative s pi over s, as long as s is positive. So that would be our Laplace transform of this piecewise function. So any questions on this example? Does it make sense? Okay. All right. So let me give you another tools so that when you do the homework problem, you don't struggle too much. So let's look. So I'm just gonna start you off with the question. I won't finish it. You'll finish it for homework. So what if you were computing the Laplace transform of, say, what's a good one? Oh, this one, sine. So say you're doing sine of AT. So if you were to find the Laplace transform of this function, it's funny. The integration is really funny. So I want to help you out just a little bit. So at least you can do the homework peacefully without going through a lot of struggle and pulling hairs. That's not pretty. So math should be peaceful, not stressful, right? So let's try this. So we want to plug this into the definition. So we have the improper integral 0 to infinity. F of t is sine of at, so we have sine of at times e to the negative st dt. Oh boy, so how do we integrate this? So if you do by parts, what happened? Do you get the answer right away? No. You have to do it several times, and then somehow the integral will repeat itself while you're integrating. So we call this the circular integration, right? You start adding, subtracting, solving for the integral. So hopefully you remember that from the past. Now you can avoid that. So, question? Does someone have a question? Okay, I'm assuming no. So you see how it's probably gonna take you like 3 or 4 integration by parts to really get to the answer. But we can do better than that. We have other tools to help us out other than integration by parts. So this is when you want to remember this formula. So do you guys remember? So let's recall Euler's identity. E to the so you remember e to the I theta, right? What is that identity? So if you remember from Euler's identity, this is cosine theta plus I sine theta, right? We had that in the past. So what I'm going to do is I'm going to rewrite e to the I theta in this way. So I'm going to rewrite e to the I, let's call it AT, okay? So the angle theta I'm going to use is AT instead of theta. So you can modify this using Euler's identity as cosine of AT plus I sine of AT. Okay, cool. Now what about if I put e to the negative IAT? Well then, again, using the same idea, your theta is now negative AT, right, times I. So you will have cosine of negative AT. Well, we know cosine of a negative angle is always positive, so I can actually ignore that. So follow me, okay? If you need me to explain that, let me know. So this is cosine of just AT. And then for sine of negative AT, what happens? Which identity do you use to simplify that? Right. Absolutely. So this is what we get, because cosine of negative theta is equal to negative sine theta. And here our theta is AT. Well, now, what do we want? We want this piece, right? We want to solve for that. So what I'm going to do is I'm going to add these up. Or actually, hold on. Let me just think for a second. I'm going to subtract them. You'll see why. So I'm going to do the first minus the second. Okay? So if I do that, so I'm doing first minus second. So if I do that, I have e to the iat minus e to the negative iat is equal to, well, if I subtract them, the cosine at minus cosine at goes to 0. So I have sine at minus sine at, so I get 2 of those. So I have 2i sine of at. And then to solve for sine at, I just have to divide by 2i. So therefore we say sine at can be replaced with e to the iat minus e to the negative iat over 2i. This would help you to heaven if you plug this in here, and just by simply using laws of exponent, it would simplify so much. So try that instead of doing by parts. You guys follow what I'm trying to say? Uh-huh. So for that, you'll add the two identities. So check this out. So what if you want to solve for cosine AT, right? We're using these exponential definitions. So if I want to solve for cosine, we'll be adding the two formulas. So for cosine AT, again, you don't want to use by parts when you're integrating, so you'll do 1 plus 2. So I'm referring to these formulas I have on the right. If I add 1 plus 2, I will get e to the iat plus e to the negative iat is equal to 2 cosine at. And the sign will go to 0 because I sine at minus I sine at, 0. Happily 0. And now I can simply solve for cosine at by dividing it by 2. So we have cosine at is equal to e to the iat plus e to the negative iat all over 2. So you would use this definition for cosine if you're integrating cosine with the exponential e to the negative st. So these, what we call the complex definitions of sine and cosine. So pretty cool if you ever study complex analysis in the future, but very useful. So there you have it. You have a shortcut to integrate sine at e to the negative st, avoiding integration by parts because that's going to take you a while. You might feel stressed out by then. So don't feel stressed out. Have fun. Have fun doing these integration. They're nice. They're pretty cool. Once you finish integrating and taking the limits, the formula is really nice. So I'll have you do that for homework. So any questions on these identities? Okay, so I hope we're okay. So the next thing I want to do is prove that the Laplace transform is a linear operator. So that's what I want to do next. So So let me write down the statement. So the statement that we're going to prove is that the Laplace transform is a linear operator. Okay, well, what does it mean to be linear operator? So it means two things, okay? That if you have f plus g and you're doing Laplace transform of that, you can do Laplace transform of f. So let me just write it out. If you're doing the Laplace transform of two functions, sum of two functions, or difference, right? You can do individual Laplace transform of these functions. So f plus or minus Laplace transform of g. Just like with derivatives, if you're doing the derivative of sum of two functions, you can differentiate each term by term. Same as integration. If you're integrating f plus g, you can separate them into integral of f plus integral of g. Same idea applies to Laplace transform. The second property is of linear operator is that if you have a Laplace transform of a constant times a function, then you can pull the constant out the operator, so you have c times the Laplace transform of f. So similarly, like differentiation, if you have a derivative of a constant times a function, we're allowed to pull the constant out and then differentiate. Same thing with integration. So the statement that I'm going to prove, so I'm going to join these two into one and prove it. So what I'm going to prove is that the Laplace transform of c, so just give me a second to think. C1, let's do that. C1 f of t plus C2 g of t is equal to C1 times the Laplace transform of f of t plus C2 times the Laplace transform of g of t. So that's the statement I'm going to prove. So what I did, I joined 1 and 2 and made it into a linear combination of f and g, multiply them by the constant c1 and c2, and then I say, okay, if I were to take the Laplace transform of this, we claim that Laplace transform of the left side is c times Laplace transform of the function f of t plus c2 times the Laplace transform of g, and then we just put the two answers together. That's what we're going to prove. So here's the proof. So how do we start the proof? Well, by definition, okay? So let f and g be two functions, and c1 and c2 be arbitrary constants. Okay, so then by definition, we have the following. We know that the Laplace transform of c1, so instead of writing f of t and g of t, I'm just going to write f and g, just to cut down some of the writing. So c times f plus c2 times g is equal to the improper integral 0 to infinity, right, by definition. So this is playing the role of the function, like the big f we had inside the definition. So plugging that in, we have c1 f plus c2 g times e to the negative st dt. So just straight plugging it in to the definition, okay? Make sense so far? Okay. All right. So again, let me know if you guys want me to explain anything, because I want you to follow me through this proof and everything else as well. So, well, now by laws of exponent or by algebra, right, we can distribute e to the negative st and have the following statement. So we have 0 to infinity c1 f times e to the negative st plus c2g times e to the negative st, everything times dt. Okay, well, so this is by algebra, right? Okay, now from here, because integration is a linear operator, I can, instead of integrating two functions together, I can separate them and integrate individually. So we know that from calculus, so we can separate the integration. So we have the integral from 0 to infinity c1 f e to the negative st dt plus 0 to infinity c2 g times e to the negative st dt. We're allowed to do this because by linear because integration is a linear operator. So this is because integration is a linear operator. Okay, so that's the justification for this. Now, because it's a linear operator, I can also pull the constants out of the integration. So we have c1 integral from 0 to infinity f times e to the negative st dt plus, again I can pull out the second constant c2 integral from 0 to infinity g times e to the negative st dt. All of that is allowed because integration is a linear operator. Well, now is the magic part. This is something cool. What do you notice? What does this remind you of? Right, so this is C1, the Laplace transform of f of t, so I'm bringing back t. And what about the second one? So this right here. Right, so this should remind us that's the Laplace of g of t. And so we have proven this statement. Check. So there you go. That's the proof for the statement that we claimed that we want to show. So this was the statement, and we have shown that statement simply by using definition of the Laplace transform and using the materials we know from the past that the integration is a linear operator. So that helps us with the proof. Pretty cool, okay? I hope you find this cool as well. Alright, so any questions? Okay, so now we're going to make transition to 6.2. So this is the end of 6.1. The rest is just for you to do some more computation, sharpen up your integration technique, play around with some of the problems, how you would approach them, find quicker way of solving them as well. Okay, so just don't forget what we've been covering in previous sections. It will help you a lot. So moving on to the next part of chapter 6 is 6.2. So 6.2, we're going to study solution to the initial value problem using the Laplace transform. So solving IVP using the Laplace transform. So this is a really nice method we can use for finding solutions to differential equations. But for this, we're going to need a table, okay? And the table that we're going to use is right here. So I'm going to put this on the document as I go along. But check this out quickly. So hopefully this will make you see things better a little. So if you look at number 1 on the list, so on the left side of the table, you have f of t, right? So these are all the function of t. So you have 1, e to the at, t to the n, t to the p, ignore that. We're not going to do that one. So you can cut off number 4. 5 is important, 6 is important. Sinh, cosh, we've seen this in calculus, so they are important too. So don't forget those. And then the exponential times sine, exponential times cosine. These are the ones that I cropped from the textbook. So yeah, I didn't copy anymore. But these are the most common one, very useful. So your task is to show that you can get, if you integrate, if you use the definition, you get this formula. For this one, I showed it to you. The second one, I also showed it to you. The third one, yes, you can try that. A little tricky. Hint for number 3 is use power series. Okay, so if you get frustrated after a couple of times you integrate, use power series. It will help you so much. And then sine, cosine, you can use those. I gave you the identities, their definition in complex numbers, so that's useful. Sinh and cosh, you can look up their definition from your calculus textbook and then apply those exponential definitions. And 9 and 10, we kind of wrote them out. So this is a very useful table. Sometime on the test, this table will be given to you. Most of the time, no, because you don't need them. You can always derive them. Alright, so having said that, going back to 6.2. So that was just for, yeah. So if I want you to, so in 6.2, there's some parts you have to use this table. So if I want you to use it, I will give it to you. But if I don't want you to use it, I wouldn't give it to you. Alright, so let's do 6.1. So here, what do we want? We want solutions by using this method of Laplace transform. So now that we know Laplace transform is a linear operator, that means if I give you a second order differential equations, you can apply the Laplace transform. But before that, we need to know what is the Laplace transform of derivatives, right? We have to have a formula for that. So let's derive those. So we want to know, 1, what is the Laplace transform of y prime? So that's a big question. We haven't computed that. We computed regular functions or functions that were nice and cute, but we haven't done derivatives. But can we still work this out with the definition? And the answer is yes, right? You should see that. So let's use the definition and compute the Laplace transform of this. So by definition, right, we know that the Laplace transform of any function, it's going to be f of t times e to the negative st dt. Well, what's f of t in this case? Well, this is our f of t now, right? Y prime. So let's plug that in. So if I plug in y prime for our f of t, we have 0 to infinity y prime e to the negative st dt. Now the question is, how do you integrate this? Yep, so the way to do this will be using by parts. So let's do it. So we have to pick a u and we have to pick dv. So I'm going to pick u to be the exponential term. Okay, and I'm going to pick dv to be y prime. And then we have to fill in the rest. What is du and what is v? So if u is e to the negative st, what is du? Okay, and what is v if dv is y prime? Y, right? Because you're integrating, so it goes back to the original function. So now, what do we have? We have u times v, right? So hopefully you guys remember that, uv. So e to the negative st times y minus the integral of v du. So that's minus minus plus y times s e to the, oh, hold on. Why does it look so weird? No, okay, it's fine. E to the negative st dt, 0 to infinity, right? 0 to infinity. Okay. So that's what it looks like if we apply integration by parts. So for the first half, we have to evaluate from 0 to infinity. So I'm ignoring the limit part, but you should be writing this as a limit. I'm ignoring it just for simplicity and less writing. So if I plug in infinity for the exponential term, so focus on this. If I plug in infinity to it, what happens? It goes to 0. So you plug in infinity, and then as you take the limit of some variable, say a goes to infinity, it goes to 0 as long as s is positive. So that goes to 0. So then we have minus the bottom limit. So we have minus minus e to the 0, that's 1, and then y evaluated at 0. So that's how we can plug that in. Plus, well, now let's analyze this integral. You have the integral of, I'm going to pull out the s, okay, so that you can see it better. 0 to infinity, y times e to the negative st dt. What do you remember by looking at this? Does that remind you of something? So think of the definition we just saw like so many times. So if I tell you that this is the Laplace transform of y, would you agree? Yeah, right? So what we conclude is that the Laplace transform of y prime is equal to negative y of 0 plus s times the Laplace transform of y. So this is a formula you want to remember. But I often don't remember it this way. I remember it this way. S times Laplace transform of y minus y of 0. That's just a simpler way of remembering this same formula. Just switching the order of the negative, okay? So this is important. We're going to use this when we take the Laplace transform of the first derivative. This will be the expression we will plug in to our differential equation when we're solving. We need one more expression. We need the expression for second derivative because we're going to be solving second order. So let's do that. So let's find the Laplace transform of y double prime. So again, using the definition, right, we're going to plug y double prime in place of f of t because the function we're looking at is the second derivative. So we have the integral from 0 to infinity y double prime e to the negative st dt, straight by applying definition. Now the question is, how do you integrate this? By part. So you're going to be doing by parts again. So let's do it. So we have u and we pick dv. So again, dv I'm going to pick the second derivative and u I'm going to pick the exponential. So then du becomes negative s e to the e to the what? Negative st, right? Yep. Thank you. And then what is v? Good. So that's y prime. Well, now we use the formula for integration by parts. So this would be, so bringing this down here, we have uv, so u is e to the negative st times y, taking it from 0 to infinity, minus the integral of v du. So we have minus minus, so that's plus the integral of 0 to infinity, v, that's y prime, s e to the negative st dt. That's what we get. Well, let's look at this one more time. What happened as you plug in infinity for this exponential term and you take the limit? So we're left with negative y of the bottom limit, which is 0. Now for the second part, well, you should notice something, but I'm going to rewrite it so that you realize it looks like something. So you have s times the integral from 0 to infinity. Right, so you have it, y prime e to the negative st dt. So this, like Schumann says, this is the Laplace transform of y prime. So what do we conclude? We conclude that the Laplace transform of the second derivative, it's going to be negative y of 0 plus s times the Laplace transform of y prime. Well, we can do better than that. Don't we know what this is equal to? We just computed that, right? Go ahead. Well, you're evaluating y at 0 right here. Why would it be y prime? Oh wait, oh sorry, I'm so sorry. I'm so sorry. I plugged it in wrong, that's why. So, sorry guys. You are absolutely right. I should give you extra credit for that. I can't. You're doing great, so you don't need extra credit. Just keep doing great, okay? Keep doing great and keep catching my mistakes. So what did I miss? Where am I? uv, so v is y prime, so that's where I missed. Yep. And then what does it become? One more time. Um, okay, got it. Thank you. So then this becomes y prime of 0. Yep. Okay, now it looks good. Okay. So now, well, we know what Laplace transform of y prime is. That's from that box up there, right? So I'm going to substitute that into this formula so that you don't have to do integration by parts to get rid of this one more time. We already have that. So let's plug that in. So if I plug that in, I have negative y prime of 0 plus s times Laplace transform of y prime, which is negative y of 0 plus s times the Laplace transform of y. Oh, braces, parentheses. Okay. And then if we just distribute the s and simplify, we have the formula, Laplace transform of y double prime. It's going to be, so let me see how I would write it. Okay. So it's going to be s squared Laplace transform of y minus s times y of 0 minus y of 0. So you want to memorize this format for the y double prime of the Laplace transform. So these two boxes, make sure you remember them. Okay, so this is important and this is important. But I would go with this one because it looks simpler. Alright, so we have the tools, so now we can start solving problems using the Laplace transform. And then you can see you can continue in this passion for the third derivative, fourth derivative of y, and so on, right? But you see how the terms will just expand more and more, and then it's just going to have more terms, more complicated. But we want to keep things simple, so we will stop at the second derivative. So let's do this example. Let's start this off, and we'll probably not finish it today. We'll finish it next time, so no big deal. So here's an example I want to work on. Let's see. So example 1. So use the Laplace transform to solve the IBP, right? Initial value problem. So given y double prime minus y prime minus 2y equals to 0, and y of 0 is 1, and y prime of 0 is 0. Okay, so let me start you off with how to do this question, and then I'll give you the a summary of what's going to be on our test. So just give me a couple more minutes. So we're going to apply Laplace transform on both sides of this equation. Okay? So apply Laplace transform, right? LT is for Laplace transform. So you have the Laplace transform of y double prime minus y prime minus 2y is equal to the Laplace transform of 0. Okay. Well, now, because Laplace is a linear operator, we can take the Laplace transform of each individual terms on the left side. That's why we needed to show that earlier. Okay, that was the idea for doing that. So we know that we can do the Laplace transform of y double prime minus the Laplace transform of y prime minus 2. So again, using the property of linear operator, Laplace transform of y equals to, what's the Laplace transform of a constant? Right, 0. Okay. So now, well, do we have an expression for this? Yeah, right, we just computed, that's right there. So that's where I'm going to substitute. So Laplace transform of y double prime is going to be replaced with s squared Laplace transform of y minus s times y of 0 minus, hold on. Looks like I made a mistake one more time, so sorry. This should be prime, right? Do you guys see that? Right? Do we agree? Yeah, right. I missed the prime notation. So plugging that in, sorry for the typo. So plugging that in, we have s times y of 0 and then y prime of 0. So that's replacing Laplace transform of y double prime. And then minus Laplace transform of y prime. So, if you guys have questions. Anyone has questions? Right, so yes, I am talking. I hope you guys can hear me. So what was the expression for Laplace transform of y prime? So if you go back, that was this, s times Laplace transform of y minus y of 0. So that's where I'm going to plug in here. This is s times Laplace transform of y minus y of 0 plus, well, minus 2. Minus 2 times the Laplace transform of y equals to 0. So the idea here is to keep going, and at the end you want to solve for Laplace transform of y. So what you will get is everything in terms of s, which is what we want because that is the function big F of s. and that's what we call the Laplace transform. And we were able to do that with simple functions. Now we can also do it for second order differential equations, constant coefficients. And then if you want to find the function of t, right, you would do the inverse Laplace transform. Now from here, I'm going to finish this next time. I just want to give you an outline. Now, to solve for y, we do Laplace inverse. So this means Laplace inverse. Okay. So if you do Laplace inverse, then you're able to go back to the function of t. So you have a function of s variable, which is f of s. So after we do all of these computation on this step, plugging in the initial conditions, y prime of 0, y of 0, correctly distributing all the negatives, you have an expression L of y equal to some function of s. Now you want function of t, you would have to do the Laplace inverse. So that's when we're going to be using this table. Okay, so that's when this is useful. So any questions? Okay, so if there are no questions, so let's start. So this is where I'm going to draw the line, and here's what you're responsible for exam 2. So for exam 2, so like last time, you're going to have 10 to 12 questions, and it's going to be on Blackboard. It will appear magically at the time that I set up, so I haven't thought about what time to set it up yet. But for this exam, I'll give you the entire class period, so you'll have 1 hour and 30 minutes, 40 minutes, but let's do 1 hour and 30 minutes, so 1 hour, 30 minutes. So the exam will start at 6:10 p.m., so you'll have until 7:40. So 6. Yeah, so you'll pretty much has the entire class period except first 10 minutes, just in case anything, okay? So 1 hour, 30 minutes, that will be more than enough time to answer 12 questions, 10 to 12. And the sections for this test, it's going to start from 3.5. So we did 3.4 was on the last test, and that was, no, we didn't do that, right? We did the reduction of order. So 3.4 is going to be on this test, so Euler equation is going to be here. So 3.4, starting with Euler equation, and then 3.5, 3.6. 3.6, we talked about variation of parameters, and then we had 3.7 and 8, that was spring problems. And then from chapter 4, we have 4.2 and 4.3, where we talked about higher order differential equations and undetermined coefficients as well. And then slowly we moved on to chapter 5, so 5.1, 5.2, 5.3, 5.3 not really. I mean, you don't really have to know that. That's a quick method of getting the coefficient. If you're interested, you can use it, but not necessary. 5.4 and 5.5. So these are the required one. And then from chapter 6, just 6.1. I'm not going to put 6.2 because I wanted to run through this example before I put an example on the test, so I wouldn't do that. So this is all for the test number 2. Alright, so any questions you guys have? Any questions regards to the exam? Okay, are you guys ready for the test? Do you want an extra credit question? So usually if it's an extra credit question, it will be difficult, right? So I'm not sure how to put an extra credit question on Blackboard because the questions will come up in a random order, right? So let me think about it how I would do that. But don't do the extra credit if you don't finish the test. That's the point, okay? If you do the extra credit, you're probably not gonna have enough time to finish the actual test. So if you finish the test early, then I will put an extra credit question. But yeah, we did. Well, but we didn't have the Euler equation from 3.4, right? We skipped that. So from 3.4, if you go back, there is a section for Euler equation. So only that part of 3.4 will be on the test. So, but 3.4 talks about repeated roots and complex roots. So you kind of have to know that for the higher order anyway, right? So everything connects. All right, so let me think about the extra credit question. I'm not sure yet. But again, I encourage you, don't do the extra credit if you don't finish the test, because I think it's going to take some time for the undetermined coefficient and the variation of parameters method, and the series solution will take some time too. So, oh, submission, great question. So, yes, so I didn't write that on the note. So let me do that. So just like last time, you will be submitting your work on Dropbox. And if you submit after the deadline, I will start deducting points for every minute you're late. So work, you're going to submit them on Dropbox. And the deadline to submit them will be 8 p.m. So once you finish at 7:40, you start scanning and make sure before 8 p.m. it comes in. After 8 p.m. I'll start deducting points for every minute you're late. So after 8 p.m. point will be deducted. And also when you submit your work, make sure it's a PDF file. So most of you, except 2 students that I called out names last time, I don't know if you guys were here, make sure it's a PDF file, not pictures. So same drill like last time. I will send you guys the link probably while you're taking the test or maybe an hour before, so that way you have it. Once you finish, start scanning and upload them as soon as you're done. All right, so any other questions? One question at a time. Yeah. So make sure you submit your answer on Blackboard, and you give me the work on a PDF file, so that way I can give you credit. So remember, if you don't submit an answer on Blackboard, you lose points as well. So you have to do both. You submit and you write down the work as well. Any other questions? Yeah, I didn't post them. Oh, thank you. Sorry, I've been posting the video and I forgot. Sorry, I'll put up the notes. Which one did I miss? 16 and 17. Okay. All right, they'll be up tonight. Thank you, Greg. Yep. So any other questions, guys? All right, so we're done for today.